Welcome back to the deep dive. If you joined us for part one of the Mason's Toolbox, we were really getting our hands dirty, talking about the craft, the trowels, the levels, the actual feel of the mortar.
Yeah, the art of it.
Exactly. Today, we're putting the tools down and we're picking up the law. We are moving from the hands-on trade to the physics, the structural engineering, and, well, the code requirements that actually keep masonry standing, dry, and crack-free for a century.
That's absolutely right. We are tackling the core mission of masonry engineering, which is, at its heart, defense. Defense against its two greatest enemies, cracking and leaking.
Cracking and leaking.
The big two.
Every single prescriptive requirement in the National Building Code, every one, is a direct countermeasure against one of those two failures. We're going to be using the NBC's Part 9, which governs housing and small buildings, as our blueprint today. And our mission for you today is to give you the ultimate site-speak shortcut. If you're a foreman, a superintendent, or, just someone who wants to know why that crack suddenly formed in the corner of your basement, we are translating those legal requirements into practical actions.
We're going to show you not just what the code says you must do,
but why. Why the failure happens if you miss that 5mm measurement, or if you decide to skimp on that 150mm lap.
We should probably start with the foundational concept. How do we turn hundreds of individual brick or block units into one single cohesive wall structure? And that all starts with what happens in the horizontal bed joint.
Okay, let's unpack this. We'll start horizontally, right there in the mortar bed. When we're laying block or brick, we rely on horizontal reinforcement. We call it ladder wire or truss wire, and we typically run it every second or third course. From a practical standpoint, the way I see it, that wire is like a continuous internal belt running the whole perimeter of the structure.
That belt analogy is actually perfect. It speaks directly to the wire's main function, which is mitigating tensile stress.
Right.
Masonry is fantastic in compression. It loves being pressed down upon, but it absolutely hates tension being pulled apart, whether that's laterally from wind or, internally from the wall itself moving.
So that reinforcement provides the tensile strength that keeps the wall from literally tearing itself apart.
Exactly. We need that whole assembly to act as one.
And the code is explicit about this, isn't it? Especially when you've got multiple layers. We talk about withes, which, it's just a fancy word for a layer, right?
That's all it is.
So you might have a concrete block backup wall and a nice brick veneer facing. How does the code mandate that those two withes actually function together?
Well, a masonry wall that consists of two or more withes must be bonded or tied together. There's no getting around it.
Yeah.
And the code gives you two ways to get there. The first method is, let's call it the traditional one. You use the masonry bonding units themselves.
Yeah.
So you're laying some units across the width of the wall, physically interweaving the two withes.
Like a full header course.
Right. And if you choose this method, those bonding units, those headers, they have to comprise not less than 4% of the total wall surface area.
4%. That doesn't sound like a whole lot until you actually start calculating how often you have to lay a full header course to hit that number.
It's a lot. It's time-consuming. It dictates a very predictable interlocking pattern.
Which brings us to the second method, which is, it's what we see everywhere now.
Far more common in modern construction, yes, using metal ties. These ties get inserted into the mortar joints, and they span the cavity, securely connecting that inner and outer withe.
And the spacing on those is critical.
Oh, absolutely. The placement and the type of these metal ties are strictly regulated. The code often dictates spacing not exceeding 200 millimeters vertically and 900 millimeters horizontally, especially at critical transition zones.
That density, that spacing, it makes sure that even if you have a slight reduction in wall thickness, say at the top of a foundation wall where you're setting up for a brick ledge, that reduced section is still structurally tied to the facing material.
It prevents any tendency for separation or, instability right where those loads are transitioning.
Okay, so that's how we tie the layers together. But where the rubber really meets the road on the job site is this idea of reinforcement continuity and lap length. You can't have that continuous belt if the wire is just stopped and started.
You can't.
This is probably the biggest practical error I have to troubleshoot all the time. You're running ladder wire, you get to the end of a piece halfway down a wall, and the instinct, the easy thing to do is just to push the next piece up against the end of the first one and just keep laying block.
And that one simple action completely negates the purpose of the reinforcement.
It's a fundamental compromise, isn't it?
It is. If you fail to ensure that continuity, what you've done is you've created an engineered weak point, a spot that will fail in tension before any other part of the wall. And the code is, it's crystal clear here. Where joints occur in the horizontal reinforcing wire, the bars must be lapped not less than 150 millimeters.
150 millimeters,
Yeah.
6 inches. That's the golden number.
It's not arbitrary.
So tell us why. What is the actual engineering failure that happens if a crew decides, 100 millimeters is good enough?
That question gets right to the heart of it. It comes down to something we call bond strength development. Think of it this way. The mortar has to adhere to the steel wire. It has to grip it.
Right, like glue.
Exactly like glue. And when that wall gets stressed, when it gets pulled, the load needs to transfer smoothly from the end of the first wire through the surrounding mortar and then into the start of the second wire, all before the wires themselves separate.
So if the lap is too short?
If the lap is too short, say only 100 millimeters, the surface area of contact between that wire and the mortar is just insufficient. It can't develop the bond strength it needs to carry the full tensile load of the wire.
So if the wall starts to move, that tensile stress hits that short lap, the mortar bond breaks almost immediately.
Instantly.
The two wires pull apart, and that separation point becomes the exact location for the vertical crack we see on the outside of the building.
Precisely. The failure initiates right at that insufficient lap. You've broken the continuous structural chain. That 150 millimeter minimum provides the required length to develop the full bond strength in standard Type N or Type S mortar.
It's a non-negotiable measurement.
It's the law on site.
Okay, so we've contained the horizontal movement within the wall itself. Now let's talk about the massive forces coming from beneath the wall. I mean, one of the single greatest causes of masonry failure and cracking isn't gravity. It's that differential movement from the soil.
That's so critical. The structure has to be designed for these load dynamics. The code is very firm on this. It says where soil movement caused by changes in moisture content, freezing, or chemical microbiological oxidation is known to occur to the extent that it will damage a building, measures must be taken to preclude that damage.
So we have to understand those three things: moisture, freezing, and chemicals.
Deeply, yes.
All right, let's start with moisture-induced movement. Heaving and settling. What conditions on a site are setting us up for that kind of cyclical movement?
The primary culprit is always the soil composition, particularly high plasticity clay soils.
The sticky stuff.
The sticky stuff. Clay soils absorb water like a sponge. So during wet seasons, they expand significantly. That expansion causes heaving, which exerts this incredible upward pressure, often cracking foundation walls or slabs from below.
And then the opposite happens in the summer.
Exactly. During extended dry periods, or maybe you have big mature trees nearby with massive root systems drawing out moisture, the clay dries out, it shrinks, and that causes settling.
I've seen cracks run diagonally clean up a wall because one corner of the building settled 2 inches while the rest of it just stayed put. That kind of differential movement is absolutely deadly for masonry that isn't reinforced.
It is.
Which really reinforces why proper grading and drainage, getting the water away from the foundation, is job number one. If you don't control the water, you are basically guaranteeing cyclical movement.
You are. The second mechanism is frost action, or what's called ad freezing. And this is a highly aggressive force.
Ad freezing.
Yeah. When water freezes in the ground, it forms what are called ice lenses. If those lenses adhere, or ad freeze to a cold foundation wall, they exert a massive upward pressure as they grow. They are literally trying to lift the foundation right out of the ground.
And that causes, again, that damaging differential movement.
Significant damage.
So how do you practically prevent that lifting? I mean, we all know we have to bury footings below the frost line, but if the soil is literally clinging to the side of the wall, that might not be enough.
It might not be. And the code actually suggests that preventing heat loss from the conditioned basement space is often the solution.
Wait, so heat leaking out of the basement is a good thing?
In this specific scenario, yes. Heat loss through a cast-in-place concrete or an exterior insulated block foundation usually keeps the exterior wall surface just warm enough to prevent the formation of those aggressive ice lenses.
So the risk goes way up if it's an unheated space like a crawl space or a cold cellar.
Dramatically. Or if the insulation is placed only on the interior of a hollow block wall, that allows the outer face of the block to reach freezing temperatures, and that's where the ad freezing can happen.
Interesting. So the heat is actually a defense mechanism.
It is. And in really severe situations, the installation of semi-rigid glass fiber insulation on the exterior has been shown to not only provide a drainage path, but to also absorb or buffer some of those physical ad freezing forces. It acts like a slip joint against that aggressive lifting.
A separation layer.
Right.
Okay. So the third threat is the one that's, I think, the most unsettling because it's a chemical reaction, not a physical one. Pyritic shale. What is going on in the earth that can create a volume increase just from being exposed?
Pyritic shale, which contains iron sulfide or pyrite, is perfectly stable until it encounters oxygen and moisture, which of course happens when you excavate and backfill.
Right.
This triggers a chemical microbiological oxidation process. Essentially, the pyrite rusts and hydrates, and that chemical reaction causes a massive volume increase. The ground literally swells up.
And that expansion can exert incredible pressure, heaving foundations, floor slabs, driveways.
Months or even years after construction is finished.
That sounds like a silent, catastrophic time bomb.
Well,
How much of this stuff in the soil is dangerous? What's the concentration we're worried about?
that's the scary part. The consequences are so severe because the necessary concentration is incredibly low. As little as 0.1% by weight in the soil can cause damage. So the code is absolute on this. Material containing pyrites must not be used for backfill or as a supporting element. If you even suspect it's there, testing is mandatory to identify and isolate it.
That's a powerful lesson. Structural integrity starts not with the block, but with the dirt you're putting it on.
That's right.
Okay, so moving up, we transition from the soil to the block itself. What are the minimum requirements for the actual structural material we're using in residential foundations?
For a standard concrete block unit, the prescriptive requirement is that it must have a compressive strength over the net cross-sectional area of the block of not less than 15 MPa.
15 megapascals?
That rating is the baseline assurance that the unit can handle the vertical load paths from the entire structure sitting on top of it.
We have to verify that unit strength. But the wall doesn't just end there. It has to connect to the house structure above. That connection is vital. That's the hinge point.
And that hinge point, the sill plate, has to be positively anchored. Anchorage is typically achieved using anchor bolts, which have to be not less than 12.7 millimeters in diameter. That's a half-inch bolt. And spaced not more than 2.4 meters on center.
But the critical factor is engagement, isn't it? You can't just drop a short little bolt into the top course of a hollow block wall.
Absolutely not. These bolts must be embedded not less than 100 millimeters in the foundation material.
100 millimeters, 4 inches.
That embedment length is critical because it ensures that when you tighten down that sill plate, or when lateral loads from wind or seismic events try to pull the structure off the foundation, the bolt doesn't just pull out.
It's all about pull-out resistance.
A 100 millimeter embedment provides enough surface area to develop that required pull-out resistance, but only if the surrounding block cells are adequately filled with grout or concrete.
And I've seen it. Short bolts just hammered into partially filled hollow cells. That is a classic failure waiting to happen. The minute you try to torque that nut, the bolt either spins or it pulls right out.
Proving that 100 millimeter minimum embedment in a solid material is non-negotiable.
And we also have to think about what happens when we step the foundation wall down for cladding, to create that brick ledge.
Right. If the top of the foundation wall is reduced in thickness for that reason, the reduced section has to be not less than 90 millimeters thick.
Yeah.
And critically, that reduced section has to be tied to the facing material with the prescribed metal ties we talked about earlier.
And the space between them.
It has to be filled with mortar to ensure stability and a uniform load transfer path. No voids.
All right, now we pivot from structural stability to moisture control. And this is where I find site terminology gets really sloppy. Everyone calls that black coating on the basement wall waterproofing.
Mm-hmm. Everyone does.
But the code draws a thick and frankly expensive line between two very different processes. And the key is understanding just how aggressively the water is attacking that wall.
The code's distinction is fundamental. It's because it dictates the performance required of the material. And it all comes down to one thing: the presence of hydrostatic pressure.
Hydrostatic pressure, so water actively pushing against the foundation wall.
That's it.
Okay, so let's define the difference clearly. When do we get to use damp proofing?
Damp proofing applies where the exterior finished ground level is higher than the interior ground level, and this is the important part where foundation drainage is provided. This system is designed to control the ingress of soil moisture.
So capillary action, humidity, simple dampness.
Exactly. It does not and it cannot resist the force of standing water.
So if your drain tile is working perfectly, damp proofing is there to handle the ambient wetness in the soil.
That's its job.
What about on the horizontal surfaces, like the slab on grade? What materials are specified for damp proofing there?
For floors on ground, the damp proofing is primarily acting as a vapor barrier. It has to consist of polyethylene, not less than 0.15 millimeters thick.
The pol
And just like with our horizontal wire reinforcement, continuity is paramount. The joints in that poly must be lapped not less than 150 millimeters.
That thin sheet of poly, properly lapped, is what stops that vapor drive from the soil from getting to your flooring or causing condensation issues inside the envelope.
And that 150 millimeter lap on the poly is fighting vapor. If you skimp on that lap, you've basically created a chimney for ground moisture to come straight into the house, no matter how good your wall coating is.
Now compare that to waterproofing. This is the heavy-duty stuff.
This is the heavy-duty defense. It applies to any below-ground wall, floor, or even underground roof that is subject to actual measurable hydrostatic pressure.
So this means the foundation is either sitting in a known high water table or the surrounding soil is so saturated it's creating a column of water that's pressing against the structure.
Right. If you dig a hole on your site and water just pools in it and stays there, you are dealing with hydrostatic pressure.
And that simple black damp-proofing coating is completely inadequate at that point.
Totally inadequate. You need a robust membrane system that is specifically engineered to resist that continuous water force.
And critically, even the best waterproofing system is still totally reliant on the drainage system.
Absolutely. Dam-proofing only works if the foundation is properly drained. The code requires that the bottom of every exterior foundation wall must be drained by tile, pipe, or a granular layer. Without that, the entire system is compromised.
The perimeter drain tile is the system's relief valve. It prevents hydrostatic pressure from building up in the first place, making sure that even a waterproofed basement isn't constantly battling this immense force. So where does all that water go?
The drains have to terminate at an approved disposal point, a sewer, a drainage ditch, or a dry well. If gravity drainage is impossible, then a sump pit is required.
And the code is pretty specific about the size of that sump pit, right?
Very specific.
Yeah.
It has to be not less than 750 millimeters deep and not less than 0.25 square meters in area. And furthermore, it must be provided with a tight-fitting cover.
And that cover is not just for looks. It ties directly into the building envelope performance. It prevents soil, gas-like radon from getting into the house.
So it's a gas barrier and a moisture management device at the same time.
Now let's talk about a common site practice. Using exterior insulation for moisture control. We see high-density mineral fiber board or, crushed rock used externally all the time.
We do. And the code recognizes that this acts as a valuable drainage layer between the wall and the surrounding soil. It helps facilitate the quick drainage of soil moisture down to the perimeter tile.
So its advantage is that it minimizes the amount of time that water is in direct contact with the wall.
That's right. But here is the critical clarification that is so often missed on site. The installation of that drainage layer, whether it's fiberboard or granular fill, does not eliminate the need for the primary waterproofing or damp-proofing membrane that the code specifies.
It's an add-on, not a substitute.
It is an auxiliary protection layer, not a substitute for the principal moisture barrier. You must layer your defense.
Okay, so if you're using the black coating, the damp-proofing, you still need the membrane. If you're using a robust waterproofing membrane for hydrostatic pressure, you still need the perimeter drain tile to minimize the head pressure. It's all about building a multi-layered defense system.
Exactly. Moving above grade now, we have to address the leaks that occur not due to groundwater, but due to precipitation entering the wall system. Masonry walls will inevitably leak where their continuity is interrupted.
At windows, doors, and the base of the cladding.
Right. And this is where flashing takes over water management.
Flashing is, it's essentially creating internal gutters inside the wall system. It captures water that gets through the exterior face of the masonry and it routes it back out. But the placement and the geometry have to be perfect or you're just inviting disaster.
The locations for flashing are prescriptive. They're non-negotiable. Flashing must be installed in masonry and masonry veneer walls, beneath jointed masonry windowsills, over the back and top of parapet walls, beneath weep holes, and over the heads of door and window openings.
Especially when they're highly exposed to rain.
That's a great point. The code recognizes that exposure. If the vertical distance between the top of the window frame and the bottom of the eave exceeds 1/4 of the horizontal eave overhang, you must have head flashing.
That's the code saying, look, if there's no roof overhang protecting this window, a ton of water is going to be dumping right onto it, so you better be prepared.
It's preventing a predictable failure. Now, let's focus on the working part of the flashing, the point where it actually expels the water, usually beneath the weep holes. The code gives 3 critical geometric requirements for how that flashing gets installed.
Let's break those down one by one and talk about the practical consequence of getting them wrong.
Okay. Requirement 1. Bedding and anchorage. Flashing beneath weep holes in a cavity wall must be bedded not less than 25 millimeters into the inside wipe.
So it's locked in.
It's locked in. This anchors and seals the flashing to the backup structure, making sure water can't just bypass it and get to the interior.
So it's not just a loose flap of metal sitting in there. It's physically engaged with that primary structural layer. If it wasn't, water could just flow around the back edge.
Exactly. Requirement 2. The drip edge. The flashing must extend to not less than 5 millimeters beyond the outer face of the building element below the flashing. This tiny 5 millimeter extension creates the physical drip edge.
And that tiny 5 millimeter detail is the difference between success and total failure. If I miss that 5 millimeters, what is the actual physics that brings water back into the wall?
It's surface tension and capillary action. Water adheres to the surface it's flowing over. If the flashing ends flush with the masonry face, surface tension keeps the water clinging to the bottom edge.
And then it just runs back.
When it reaches the vertical face of the masonry below, capillary action, the tiny spaces between the mortar and the unit, sucks that moisture right back into the wall system. That 5 millimeter projection forces the water droplet to form and break free of the surface tension, dropping clear of the wall.
The drip edge is the spout on the gutter system. It has to break the physics of water adhesion.
That's a perfect way to put it. And requirement 3, the slope. The flashing must be installed with a nominally horizontal slope toward the outside wipe.
And this is where we get the danger of the reverse lap.
Yes.
If that flashing slopes inward, even slightly, maybe because of a big mortar dropping or just poor installation, you have intentionally routed every single drop of water you collected directly toward the inner structure and the house framing.
You've turned your water interceptor into a water delivery system. It is catastrophic. We have to ensure the flashing extends from the front edge of the masonry up behind the sill or lintel, covers the full width of the opening, and always maintains that outward pitch.
Okay, beyond the flashing detail itself, we need to talk about the space, the air gap. This is the capillary break that really defines a modern rain screen approach to masonry.
Absolutely. The wall assembly is deemed to have a capillary break between the cladding, the brick or stone veneer, and the backing assembly, the sheathing and structure, if there is a drained and vented airspace not less than 9.5 millimeters deep, so just under half an inch. And it has to run the full height and width of the wall.
And that 9.5 millimeter minimum airspace is the critical gap that stops moisture transfer. Water vapor, condensation, any liquid that gets through the face, it all has to be able to drop straight down that gap to the flashing.
We also see variations in the required size of this drainage space depending on the structural type. For masonry veneer walls, the required drainage space is often cited as 25 millimeters or 1 inch. And for full cavity walls, where that cavity is the primary defense, the spacing can be 50 millimeters or 2 inches.
Why the bigger gap?
The increase in size accommodates a greater potential for debris accumulation and ensures a more robust ventilation and drainage path.
Which brings up a great point. What happens if that cavity gets bridged, say by excessive mortar droppings falling to the bottom, or by wall ties that haven't been treated with a drip leg?
Bridging the cavity completely defeats the purpose of the capillary break. Mortar droppings, or bridging, create a physical connection between the outer wet surface and the inner sheathing. Water then bypasses the drainage plane and is sucked straight across that gap by capillary action.
So even with a 15 millimeter cavity, job site cleanliness is still paramount.
It is. The whole system is a series of layers. The cladding takes the initial hit, the air gap breaks the capillary action, the continuous flashing acts as the gutter, and the drip edge acts as the spout. If you skip one single step, the entire system fails.
All right, let's shift gears completely now to structural heavy lifting. Let's talk about the vertical steel and the grout that turns a simple stack of hollow units into an earthquake-resistant system. This is where discipline and material quality become the law.
This is non-negotiable structural integrity. The requirement for reinforcement is tied directly to location and seismic risk. For load-bearing masonry buildings up to 3 stories high in specific seismic zones where the ground movement intensity is high, reinforcement is mandatory.
You used some jargon earlier. Spectral acceleration SAP 0.2 is greater than 0.35. For our listeners who aren't structural engineers, what does spectral acceleration mean in site speak?
Spectral acceleration, SAF 2, is essentially a measure of the expected intensity of ground shaking, the jolt, at a specific frequency that is particularly damaging to short, stiff structures like masonry walls.
So it's how hard the ground is expected to shake the building.
In a specific way, yes. If that expected jolt intensity exceeds that prescribed threshold of 0.35, the code mandates minimum reinforcement to prevent a catastrophic lateral failure during an earthquake. That steel provides the ductility and tensile strength needed to hold the wall together.
So if you're building in a known tremor-prone area, that steel isn't optional for structural elements. It is the life safety mechanism.
It is.
And when we put steel into masonry, the quality of the matrix around it, the mortar and the grout, is paramount. And this is where we bring back the golden rule.
The golden rule is simple. The building code is law. What the old-timer on the job told you about how much water to add to grout doesn't matter if it violates the prescriptive requirements for structural performance.
So what are those requirements?
For reinforced block foundation walls, the mortar must be a high-strength type S. And furthermore, the grout used to fill those cells has to meet the rigorous standards of SECANT CSA A179.
Okay, let's focus on grout quality. We need the grout to flow easily so it fills every single void around the rebar, but we can't compromise its compressive strength. What's the material standard that gets violated most often on-site just for the sake of flowability?
The critical standard is the water-to-cementing material ratio. For concrete mixes used in walls, which includes the grout for foundation walls, the maximum ratio shall not exceed 0.70. That is a hard limit.
So what happens when a crew wants the grout to flow like water, so they dump in too much and they blow past that 0.70 ratio?
Well, you might achieve flowability, which makes placement easy, but you have drastically weakened the resulting concrete column. Overly watery grout, we call it soupy grout, violates the structural material standards.
What does that dilution do?
It leads to excessive shrinkage, segregation of the aggregates, and ultimately a significant reduction in the final compressive strength. You might satisfy the visual inspection that the cell is filled, but the column of concrete you created is structurally compromised. It cannot carry the loads the engineer designed it for.
You're essentially pouring muddy water. You lose the entire benefit of having that steel encased in a high-strength load path.
Exactly. Next, we have to focus on rebar placement and continuity. The steel needs to be in the right place, and it needs to be continuous. For example, in flat insulating concrete firm foundation walls, the code specifies that vertical reinforcement has to be located in the inside half of the wall section,
The inside half.
with a minimum cover of 30 millimeters from the inside face of the concrete.
Okay, the 30 millimeters of cover is for corrosion protection. But putting the rebar on the inside half, that's a strategic decision. Why is it positioned there?
It's positioned strategically to resist the lateral earth pressure coming from the outside. That pressure puts the inside face of the foundation wall into tension. So the reinforcement is placed on the tension face to carry those pulling loads.
And what about around openings?
The code requires continuity around weak points. When reinforcement is interrupted by a window or door opening, the bars must be placed not more than 600 millimeters from each side of that opening to maintain lateral resistance right where the structural wall is naturally weakest.
Okay, now for the practical troubleshooting, let's talk about the missed bar scenario. You inherit a wall that's 8 feet high, 2.5 meters, and the inspector notes you missed a critical vertical bar required by the design. The knee-jerk reaction is to grab a hammer drill, shove a piece of rebar into the cell, and fill it. Why is that a code violation and a structural risk?
Because the reinforcement system requires anchorage and continuity. If that bar wasn't properly anchored at the footing, embedded into the slab or the foundation below, and correctly tied to the subsequent vertical bars, it cannot transmit the intended tensile load.
So it's just a piece of metal sitting there.
It's a structural fiction. A bar that's just hammered into wet grout or even epoxied into a finished floor without the proper specified lap length or anchorage detail cannot perform the job required by the engineer for seismic or lateral stability.
The law requires proper placement, anchorage, and material integrity.
Rushing or improvising means you sacrifice the engineered strength.
And that leads right back to what we talked about in Section 1, lap splicing. If we have two vertical pieces of rebar that need to meet, they have to be lapped properly. The common rule of thumb is often, 40 times the bar diameter?
That 40 diameter rule of thumb exists for the exact same reason the 150 millimeter lap exists for the horizontal wire. It provides sufficient surface area for the bond between the steel and the grout to fully transfer the tensile load from the end of one bar to the start of the next.
If your lap is too short, the splice just pulls apart under load.
You have two pieces of steel that cannot act as a single continuous member, which leads to structural failure.
Finally, let's connect this all back to the very top of the foundation wall. You have to secure the sill plate, and you're often dealing with hollow block.
Right. And when you're fastening that sill plate with anchor bolts, the stability relies entirely on the strength of that top course. For hollow block unit masonry foundation walls, the cells directly beneath the sill plate must be filled with concrete or grout.
No exceptions.
No exceptions.
Uh,
This provides the solid bearing necessary for those anchor bolts to achieve their 100 millimeter embedment, and it ensures a consistent, continuous load path down to the rest of the wall. Without that grout filling, the anchor is just sitting in an air pocket waiting to fail.
So we have spent the last half hour or so detailing the system requirements necessary for masonry defense.
We have. We've covered everything from ensuring horizontal reinforcement is lapped 150 millimeters for continuous tensile strength, to managing catastrophic soil movement, whether that's heaving or the chemical expansion of periodic shale.
We established the vital difference between fighting soil moisture, which is damp proofing, versus hydrostatic pressure, which is waterproofing.
And we detail the precise geometry required for flashing, including that critical 5 millimeter drip edge to defeat capillary action.
The knowledge nugget here, I think, is continuity. Whether it's the physical tie of the reinforcement, the unbroken plane of the damp-proofing membrane lapped 150 millimeters, or the proper pitch of that internal flashing gutter, masonry failure is almost always a break in the system's continuous chain of protection.
That's a great way to put it. We're engineering continuity into what is, by its nature, a discontinuous material.
And this commitment to continuity is present in every section of the code, even in places you might not immediately connect to the masonry structure. I mean, think about the air barrier system.
Right. The code requires that the air barrier must be continuous and sealed around all penetrations, electrical, piping, ductwork. And that's not just about energy efficiency. It's about preventing internal air movement that could carry warm, moist air into the wall cavity, leading to hidden condensation and internal structural moisture issues.
So preventing condensation is structural defense. But I think the most insightful example of this comprehensive defense is the floor-on-ground slab. The code demands sealing penetrations in that slab in a very specific way. It has to prevent the upward flow of air.
To stop soil gases like radon.
Right, while at the same time allowing for the downward flow of liquid water.
That requirement, which is often met through specific trap designs and sealant applications around floor drains, it just demonstrates that the code is fighting gas, vapor, and liquid water all at the same time. It recognizes that failure in any one of those three domains compromises the entire basement environment and potentially the structural elements.
Okay, now here's a provocative thought for you to carry into your next project scope. We know the code is the ultimate authority, and it requires you to understand the ground you build on. The soil section of the code contains a specific, and I think a hidden, clause regarding foundation bearing capacity. If a foundation is located in an area where high water tables are known to occur, meaning the footing is bearing on gravel, sand, or silt, and the high water table is within a distance below the bearing surface equal to the width of the foundation, the allowable bearing pressure of that soil is automatically cut in half.
A 50% reduction in the structural capacity of the soil itself.
That single simple proximity clause, the water table depth relative to the footing width, changes the entire engineered capacity of the foundation. How does that hidden clause change how you scope a foundation job, how you interpret a geotechnical report, and how you manage your excavation even before the first block or yard of concrete is ever delivered? It means managing water isn't just about preventing basement leaks, it's about protecting the core structural stability of the entire building. Think about that the next time you look at a wet excavation. Until next time, keep digging deep.